Next up we have Lukas from the University of Tübingen, and he will talk about the geometry of sine gradient descent.
Yes. Yeah, thanks a lot for the opportunity to speak here. I'll be talking about our work on the geometry of sine gradient descent with Fabian Pedregosa from Google Brain and Nicolas Leroux, also from Google. This talk, I guess, is a bit of an outlier because it's a talk about optimization. We assume that we actually have an objective function f that we want to minimize, like in good old times. So we have a function f that we want to minimize with respect to the parameters x of some neural network. And we are going to compare two methods, good old gradient descent, which you all know, and then a method called sine gradient descent, which takes your gradient vector and then it applies the sine operator to each element of the gradient vector. So now you have a vector of all plus or minus ones, and the negative of that will be your update direction. And this method has received some interest in recent years, as evidenced by this bunch of papers down here. And why is that? It seems the idea of sine gradient descent seems silly at first. Why is it interesting? So one aspect is that in a distributed optimization setting, it's actually very useful to have the vector that you have to transmit between workers to be 1 bit per coordinate only. So in distributed optimization, sine gradient descent drives down communication cost. But it's of interest beyond that because there's a relatively close connection to the so-called adaptive gradient methods like Adam, Addergrad, etc. Because all of these methods normalize gradient coordinates individually. So they all do somehow like equal update magnitudes for each coordinate, similarly to sine gradient descent. And then maybe the most convincing reason is that it just shows a very good practical empirical performance. So in this plot from our 2018 paper, you can see sine gradient descent in this greenish curve basically be on par with Adam, that's the orange curve, across a bunch of deep learning tasks. And both these methods often outperform gradient descent-based methods in red and blue here. Right, and the purpose of this work was exactly to understand when and why this can happen. When does sine gradient descent work better than classical gradient descent? And of course, there's multiple possible aspects to this. It might have to do with the non-convexity of the objective, escaping saddle points, etc. Or maybe it has to do with robustness against the stochasticity in the gradient evaluations. But maybe it's also just plain old considerations about curvature of the objective function. And that's the aspect we are focusing on, because we realize that there's something to be understood about the relative performance of these two methods, even in deterministic quadratic problems. And that's what I'm going to be talking about. So for the rest of the talk, we will ignore stochasticity, and for the most part, we will also assume the function to be convex. And I'm going to give you the conclusions in advance, or a preview at least, which is that sine gradient descent can outperform gradient descent if the objective is somewhat aligned with the coordinate axis, and if the Hessian of the objective is dominated by a very small number of outlier eigenvalues. Sorry. And if we have dense gradients. And I'm going to explain what I mean by all of these things in the course of the talk. And to derive these insights, we are going to embed the two methods, gradient descent and sine gradient descent, in a common framework and analyze them within this framework. And that framework is steepest descent with respect to arbitrary norms. And to derive that, we will assume the objective function to be smooth with respect to that arbitrary norm, which, as you probably all know, means that the gradient is Lipschitz, which means that the change in gradient, if I go from x to y, is bounded by a constant times the change in parameter space. But note that the change in gradient is now measured in the dual norm of the originally specified norm. And I'm sure most of you will be familiar with that. Smoothness gives us local quadratic bounds. So around my current iterate xt, I now have a quadratic bound on the function f evaluated at x, and the quadratic contribution is now in this arbitrary norm that we specified. And steepest descent is any method that chooses the next iterate to be a minimizer of this bound. Okay. And as I already said, both gradient descent and sign gradient descent fall within this framework. And gradient descent is steepest descent with respect to the Euclidean norm, as you would expect. The Euclidean norm is dual to itself, and the resulting update is the gradient descent update. And sign gradient descent turns out to be steepest descent with respect to the L infinity or maximum norm, whose dual is the 1 norm. And the resulting update is sign gradient descent. Okay, so, and we can analyze all steepest descent methods jointly without specifying the specific norm. And there's all kinds of convergence results for that, but they basically all are based on this little lemma here, which says that if your function is smooth with respect to that norm, a single step of the corresponding steepest descent method gives you a guaranteed decrease in function value, which is given by this ratio of the squared gradient norm divided by the smoothness constant with respect to that norm. So if we want to compare gradient descent and sign gradient descent, we have to compare these two quantities. And if we take their ratio and regroup the terms, we get the ratio of gradient norms, 1 norm divided by 2 norm, both squared, and then the ratio of smoothness constants. And from just basic inequalities between the 2 norm, the 1 norm, the L infinity norm, we know that this ratio will be anywhere between 1 and d. So the 1 norm is always larger, and it can be up to d times larger. And the ratio of smoothness constant is between 1 over d and 1. But that means that the ratio that we are interested in is anywhere between 1 over d and d. So we don't know how things will play out. All right, and then this ratio of gradient norms is one of the aspects I mentioned initially, and because it relates to the gradient density. So this ratio will be large, which is favorable to sign gradient descent, if the gradient vector is dense, like it's a densely populated vector. But that's basically going to be all I will say about this gradient density, because this is a local property, right? It depends on the gradient evaluated at x. And we can't really bound it globally or anything. And we are going to focus on this ratio of smoothness constants, which are global problem properties. And I will show that this will be favorable to sign gradient descent. So this will be, L infinity will be much smaller than its worst case of d times L2, if the other two aspects I mentioned initially are fulfilled, if the objective is axis aligned and there are outlier eigenvalues. And to see that, we have to understand what drives these two smoothness, which properties of f drive these two smoothness constants. And if f is twice differentiable and convex, we have a very good intuition for the Euclidean smoothness constant, right? We know that it arises as a bound on the spectral norm of the Hessian of the objective. And for positive definite matrices, the spectral norm is simply given by the largest eigenvalue of the matrix, right? So you know what property drives the Euclidean smoothness constant. And what we show in the paper is that similarly, the L infinity smoothness constant is a bound on the Hessian, but in a different matrix norm. And this different matrix norm is defined implicitly, and it's actually NP hard to compute. But we have an upper bound, which is a product of two terms. One is the sum of all eigenvalues of the Hessian, of the matrix. And then the other one is the inverse of a quantity which we call rho diagonal. And rho diagonal just measures the proportion of mass of this matrix H, which sits on the diagonal as opposed to the off diagonals. And this quantity rho diagonal relates exactly to the property of axis alignment. And we see that in simple two-dimensional quadratics, which we visualize by the ellipse, which is formed by their contour lines, basically. And we have a bunch of quadratics here, and we vary we fix the first eigenvalue to be 1, and we vary the other eigenvalue between 2 and 4. And we also change the rotation angle of this ellipse. And we see that L infinity grows as we get further rotated away from the coordinate axis, basically. Okay, and with this bound, we can now answer the question of when is this L infinity thing not too big compared to L2, which would then suggest that sine gradient descent can be competitive with gradient descent. So we will compare lambda max to this row diagonal to the -1 times sum of eigenvalues. And this condition that we want is fulfilled if row diagonal is large, so that's the axis alignment aspect. And then the other condition would be that the sum of eigenvalues is much smaller than its worst case, which would be d times lambda max. And another way of writing this is to say that the average eigenvalue is much smaller than the maximal eigenvalue. And this relates to the presence of outlier eigenvalues. So we want a large number of small eigenvalues which make the average eigenvalue small, and then a few, or in the ideal case, only one large eigenvalue, lambda max, which really drives this ratio of lambda max to lambda bar very high. Okay, and this, that's a theory, and now we look at results on simple quadratic problems. So each point in this plane is a quadratic problem, and we vary the two relevant properties, the ratio of lambda max over lambda bar, and then some rotation angle theta. And we see that this left plot is the ratio of smoothness constants. Of course, L infinity is always larger than L2. But in this regime where lambda max is far exceeds lambda bar, but we're somewhat axis aligned, so the top left regime, L infinity is actually very close to L2. And then the performance of the two methods, so we run the two methods, and you can just think of this as some measure of performance, where pink values correspond to sine gradient descent being better, and green values correspond to gradient descent being better. And we see that exactly in this regime, sine gradient descent can drastically outperform gradient descent. Whereas for non-axis aligned or mildly conditioned problems, it's the other way around. There was a question, I think? Yeah.
When you say better, both methods find the exact same solution,
right? Right. Yeah, this is, I mean, faster in that for some fixed number of iterations t, this value was smaller for sine gradient descent than for gradient descent.
But at the end, they both find the
right, this is a quadratic problem, so there's only one solution. All right, and then of course the big question is whether this theory actually is pertinent to what happens in neural network training, in neural network optimization, I should say. And I can't go into the details on this, but there's actually literature out there that suggests that both of these phenomena are actually present in neural network training objectives. So both on the outlier eigenvalues in the Hessian spectrum and about this axis alignment, there's literature out there suggesting that this is relevant. And we also did some first initial experiments to also check this for ourselves. So what we're doing here is we pick two different deep learning tasks. They are both on the CIFAR 10 data set. The top row is a simple CNN, and we see sine gradient descent outperforming gradient descent. And the bottom row is a ResNet, and we see that sine gradient descent is the faster optimization method in this case. And then in the right column, we track this ratio of guaranteed improvements over the trajectory of the two optimizers. So we want to get some glimpse into whether this ratio actually predicts what we see in practice. And we see that for the top row, we see values of this improvement ratio which are at least close to 1, and in the initial phase larger than 1. Whereas for the bottom row, we see values that are much smaller than 1. So of course there's no perfect correspondence, but this suggests that this theory based on the smoothness constants and the gradient norms actually is somewhat in line with what we observe in practice. All right, just to give the main takeaways again, sign gradient descent can be the superior optimization method if if three aspects are fulfilled, if the objective has some degree of axis alignment, if the Hessian spectrum is dominated by a few outlier eigenvalues, so that's lambda max much larger than lambda bar, and we see dense gradients. And that's all I have. Thanks, and I'm happy to take questions. Yep. Oh, sorry.
Could we interpret this result by somehow saying that doing this sign somehow is more similar to a second order method, like?
It's inherently a first order method.
Yes, I do. But
Yeah.
applying these signs, does it make it more the optimization path more similar to a second more order method where you add the Hessian, or so is that true or not?
I don't think that's entirely true. I guess for this subclass of problems that are very ill-conditioned and axis aligned, the updates given by sign gradient descent and a Newton step would be closer to each other than a Newton step and a gradient descent step.
Yeah.
Right. Yeah. But of course, there's no second order information incorporated into the method or anything, right?
Yeah, but what basically happens is that you go a closer path, right?
Yeah, you're closer to a Newton step than gradient descent would be under these conditions.
Thank you.
Yeah.